survey of linear algebra issues and this type of computation.
Right. So I'll talk about some of the numerical linear algebra components. So the first one is improving the scaling of QMC calculations. So most QMC calculations are done on fairly small problems. Well, small is relative, of course, for every problem. But when you think about hundreds or maybe a few thousand particles, what if you want to go to 10,000 or 100,000 particles, right? So if the scaling of your problem is not very good, that gets very expensive. And then after that, I want to talk about some eigenvalue problems, and so methods to solve them, a little bit about sensitivity and accuracy of eigenvalue problems, because it determines to a large degree how useful your answers are and how fast your methods converged, and maybe a little bit about generalized eigenvalue problems depending on the time. And then, well, we've seen in all the talks, right, computing the wave function is an eigenvalue problem, or computing the various states. So they come up, and in Jeremy's talk yesterday we saw also a generalized eigenvalue problem come up, which is then often solved as a normal eigenvalue problem. But if we get to the generalized eigenvalue problems, I'll show one method that can solve it directly as a generalized eigenvalue problem. Okay, so improving the scaling of quantum Monte Carlo, and at this we're thinking about doing this for more general materials, but right now it's really for insulators. And well, so you've seen the people kind of involved in this project, but in this particular part, it's the 4 people at the top that were specifically involved in this. So Couple was my student, and he graduated almost a year ago, and Brian graduated maybe 2 years ago. Was David's student. And then 2 new students that are starting to work on this are Li Ming and Ariel. And this is my part of the grant. We all have our own number, so because it's a collaborative grant. So, okay, so I'll talk a little bit about the scaling of the QMC importance sampling. So it's kind of funny, there's things you want to compute, but it's really the importance sampling that determines the cost right now. Then in order to make that cheaper, we'll look at certain iterative methods for solving linear systems. And so I'll give a quick introduction to Krylov subspace methods, which is useful anyway because they also play a big role in solving eigenvalue problems. Okay, so then I'll continue talking about what we actually do to compute the determinant ratios, because those are really the things you look at to determine the acceptance of a particle move, how we get it faster, and some results. Okay, so the background of this for us, and well, this is being mentioned before, right? So it's important for geophysicists to understand properties of materials very deep in the ground, right? So if you go a few hundred kilometers, there's no way you can get there, so computation is really the only thing you can do. Well, there's some seismic can tell you something too, right? And some of the methods under high pressure and temperature do not really give you the right results. So QMC needs few assumptions, and it's accurate, but it is expensive, right? So the background of this component is better algorithms for the linear algebra. And okay, this repeats what I just mentioned. Okay, just to kind of get started. So you've seen this now many times, right? So Monte Carlo for electronic structure calculation, so there's this variational optimization of functions is really what is going on. And we're working with this multi-particle wave function where, okay, R1 to Rn are the particle positions and spin, but in this talk we mostly ignore spin. And say the alphas are a set of parameters that you're optimizing over. Okay, so the wave function gives the probability of finding a particle at a region in space. And so we want to optimize some function, for example, the energy. And in this case, for simplicity, I'm going to assume that the wave function is real and it's normalized. But those are kind of details that can be handled. But the main thing here, well, for most people here, this is not a big deal, right? But for mathematicians, it's important to kind of realize that the scale of the problem, of course, is so high dimensional that a lot of standard methods that we use, like finite elements or other things, really are impossible to use, right? If you had a few points per particle in every dimension, right, it would be a few to the power 3n, and that goes very rapidly. Okay, so again, you saw this in David's talk and in some of the other talks, right? So we can turn this computation of the energy into a sampling process where we sample this local energy. but you can do this generally for all kinds of observables. And the problem, of course, is that, okay, in order to do, because the wave function takes very small values almost everywhere except at very localized regions, you need to do importance sampling. You cannot just sample space kind of uniformly. So you need to sample with the right probability. Okay. And so here is in 3 lines, like it was already a very simple algorithm when David showed it, but it was about a slide, right? So now it's in 3 lines. So we generate these configurations R, and for each of them, right, assume you have some state, you generate a random step of some size d. So d is typically very small, and the way it's written here, d could be a change in all particles at once, but in practice, we typically just move one particle. And then we need to compute this probability. So we need to accept the move with this probability that looks like this. So we need this ratio between those 2 wave functions. And okay, if it's accepted, we evaluate the observer at the new configuration. If it's not accepted, we evaluate it at the same configuration. And then we kind of move on, right? And it needs some initialization period. And as I mentioned, in practice, we move a single particle in each step. So what is this wave function? Again, this now, you've seen this many times, so we're not going to go through the details, right? But okay, so for a boson, I guess you would take single particle wave functions, assuming that they're independent. And for electrons, we take all the sum of all signed permutations of this. And so you can write this as a determinant, right? And that's the Slater determinant. And then in practice, right, you multiply this by this Jastrow factor or function. But in this case, the cost is all in evaluating the ratio of these 2 wave functions at the current and at the new position, or the proposed position, if you want. So in order to kind of just focus on the component that really matters, right, I'm going to ignore this Jastrow factor as well in the part that I'm discussing. Okay, so this is what the Slater matrix looks like. So essentially, the columns are determined by the orbitals, and the rows are determined by the particles. And so if I move one particle, right, so let's say I move the kth particle, so I went from rk to rk tilde, then obviously only the kth row will change because all the other particles stay at the same place. And so I call this vector u is then just the vector that gives the change in the kth row, or uk, or I think most of the slides is just u. So that's just the change. Now the other thing is, for insulators, if you optimize the basis functions, they tend to become localized. And so this matrix, and I'll show an example, is sparse, right? Because since the basis functions are localized, if a particle is sufficiently far away, I mean, the value is going to be either, infinitesimally small, or because you use some cutoff, you just set it to 0. I mean, that's what you do in practice, of course. So this u vector is also sparse, right? So it only have non-zeros for the orbital, so to speak, that can actually see the particle. And then with some manipulation, so we're interested in the ratio of the square, but of course we can just compute the ratio itself and then square it. So if you, with some simple linear algebra manipulation, you can show that the ratio of those 2 determinants can be written as 1 plus, okay, u transpose, but u is this vector here, times A inverse times, and ek is just the kth Cartesian basis vector. So it's a vector with all zeros and a 1 at position k. And of course it means that you can write the new A, so for r tilde is just A plus ek u transpose, right? So plus a rank 1 update. So that just changes the kth row. So, okay, so this means that rather than, say, computing those determinants directly and then dividing this or doing, there's various other things you can do, right? So we can just solve a linear system, right? So we can solve a system, say, A times Z is equal to ek, and there's slightly different things you can do. And then we can compute this ratio. Okay. Now what does the standard algorithm do? Like I said, there's many things you can do. I guess that's an order n to the 3rd that wasn't removed somehow. But so what does the standard algorithm? It maintains an explicit copy of the inverse matrix, right? So if you think about computing this thing, right? So if you have a copy of the inverse, every time you need to compute this, okay, you just take the kth column of the inverse. It's very simple. Of course, it means that every time you accept a particle move, you have to update the inverse. And of course, computing an inverse is expensive. I mean, if you do it every time from scratch, it would be n to the third work. But so you can do it slightly smarter by using the Sherman-Morrison for if it's a rank 1 update of the matrix, or the Woodbury formula if it's a higher rank. Right? And so the idea is like this, right? So A plus EKU transpose. So this is just a Slater matrix at the new position. Its inverse can be written as A inverse, which you would already have, plus, okay, this scalar. Note that this is just the same ratio we were looking for, times, okay, A inverse EK, that's the kth column of the inverse, times, okay, this thing. So this thing, you have to then take the, say, a cross product of U and every row of this matrix. So cost is measured for what is called a sweep. A sweep is moving every particle, or attempt to move every particle once. So it's kind of n of those elementary steps. You move a particle, check if you accept it or not. That's one step, so n steps. So updating this, as you can see, so even though A is sparse, right, A inverse in general is not. So A inverse EK and U transpose A inverse, there might be some cost cutting you can do there, but in general this will be an update of all components of the matrix. So this is n squared work. So that's order n better than, recomputing the inverse. So it's n squared work. But if you do this for n steps, right, it's n to the third. So I think in the old days, right, computing the matrix was order n to the third work as well, because you were summing over n basis functions for every coefficient in the matrix, so that's n squared times n. But this optimization of these basis functions making the matrix sparse has made that more or less linear. And since that was the main cost, right, people now talk about, when they make the matrix sparse, they talk about order n methods. But really, there is still an order n to the third cost in there. It's just not as high as the other cost was. And so if you want to go to large numbers of particles, so really large n, then obviously this cost is going to dominate. Okay. And so you also need to compute, right, so you need to evaluate the Hamiltonian, so there is also this gradient is in there for the momentum, and then if you want to take the derivatives for the optimization, well, actually just for the optimization you would need those, I guess, already. So it's the Hessian and the gradient. So those are similar computations. So just as we replace, say, maintaining this copy of the inverse, replace it by a solve, we can do these steps in exactly the same way. Okay, so the major cost of this algorithm is computing those ratios. And, well, okay, this just summarizes what I said. Okay, so for sufficiently localized basis functions, the matrix is sparse, and a change of basis does not change the solution to the variational problem, right? So that's the idea that you can optimize those, the localization of the basis functions. And so as I said, it reduces the computation of the Slater matrix to order n, but the determinant ratios is still n to the third, right? And so what we wanted to look at is if we can reduce this to, substantially less than n to the third, right? So n squared is our first goal. As you can see, we're almost there, and in fact, improving a few things that we had not done yet when we wrote the paper that this talk is based on. It was a little bit higher, but we can certainly get that. And then, of course, the next step would be, well, can we actually get less than n squared? That's a much more complicated question, but we're optimistic people, so we have hopes that we can do that. And the other thing, this is done for insulators. So for metallic systems, optimizing the locality may not work. And so we need to look at other ways. And of course, if the matrix is not sparse, well, you'll see that the iterative methods I'm talking about, unless you find some other way of doing a very fast matrix vector product, then will become n to the third again. So if you have dense matrices, we really have to do something different yet to kind of get the same results. So if you order the matrix in the right way, so we're interested in the determinant of this matrix, right? So the ordering of rows and columns is completely arbitrary, but if you order it the right way, which for us is important, it looks somewhat like this, right? And you can think that if you ever seen say finite difference matrix where you have kind of localized, you get something the same, and then this is from the periodic boundary conditions, right? So it's similar to that. Okay, so we want to use iterative methods to solve this linear system, because if we can do that in a modest and bounded number of iterations, we would be at n squared rather than n. I want to say a little bit about this. And Krylov spaces will come back in the eigenvalue solvers as well. And actually, David mentioned Krylov spaces as well. Okay, so for linear systems, so this is the linear system we want to solve. Ax is equal to b. I have some initial guess x naught, so I can compute what is the residual. It's just the difference between the left and right-hand side. And then I can build a space, which is just the span of all these vectors here. So these are powers of a times this initial vector r naught. And an important thing to see, and I'll emphasize that in a moment, of course, is that since these are powers of a times r naught, every vector out of this space is just a polynomial in the matrix A times that vector r naught. So you can think of this as this sequence of powers of a times r naught. You can also think of it as a space of polynomials. Okay? And one thing we can do is we could say, like, well, what would be the best updates to x naught from this space? Now there's quite a few different methods, and not all of them would want to compute this particular update C, but one of the most popular methods, GMRES for general systems, would do this. But for example, CG for symmetric problems does something slightly different. It also computes an optimal Z, but in a different norm. Right, so it's find the best Z out of this space to minimize the 2 norm of the residual. Okay, so you can write it as this. So it's just approximating the residual by AZ, where Z comes out of this space. And okay, what does that mean? If I would take a matrix K and stick all these vectors in that matrix, now that would be a terrible way to solve the problem. It would be completely unstable. So you shouldn't do it this way. Then I can parameterize the vector Z as just Km times some unknown vector zeta. But that vector zeta now is of small dimension, right? So in most cases, we think of these systems A much larger than what we're doing here. So in QMC, the systems we solve are very, very small compared to what I'm usually thinking about. But then if you have to do it a million times, right, it still becomes expensive. So usually we think of A as being, the order of, millions, or typically at the labs now, right, that may be billions even. And so M can be very small, can be 10, 20, 50, and so on. So we can parameterize Z in this way. And so now I have a least squares problem. That's really just what I'm doing. I'm solving a least squares problem for this matrix, right? A times R naught, so A times K and Z. And the idea is for an efficient algorithm to do this in a smart way. So I'll show the Arnoldi recurrence in a moment, but it computes essentially an orthogonal basis for these vectors and then projects this least squares problem, and I'll show the algorithm on the next slide, on this basis. And the nice thing is then that independent of whatever n is, right, if you do m steps of this, you only have to solve a least squares problem of size m plus 1 by m. So after you do the work of generating the basis, everything is very cheap. Okay? So this essentially was the generalized minimum residual algorithm by Youssef Saad and Martin Schulz. And well, I don't know what, yes, it has thousands of citations, right? It became a very, very popular algorithm. And, okay, I made a mistake here. Okay, so this is the same, okay, so this is the idea of this polynomial, right? So if I multiply Km times some vector zeta, and of course zeta as so far is an unknown vector, right? If you write it out, right, so you just get this linear combination. And so you can see this is a polynomial in A times R naught. And of course, unless you specify what you exactly want from this Z, you can pick this polynomial arbitrarily. Every different polynomial will just give you a different approximation. Some might be good, some might be bad, and obviously you want good ones, right? But in principle, this polynomial is arbitrary. Now the residual, it turns out, if you write this out, right, you get R naught minus A times this polynomial. So you multiply everything here by A and subtract from R naught. So that's a different polynomial, right? So the residual is a polynomial in this Krylov space as well, but it's not arbitrary, right? No matter how you pick P, you're going to get the identity here at the start, right? So it looks like identity minus A times P. So every polynomial that can represent the residual has this normalization, right? So this is not arbitrary. A residual polynomial will always take 1 at the origin. And we'll see in a moment that that's somewhat annoying if you have eigenvalues very close to the origin. So that's something we would like to avoid. Anyway, so here's the GMRES algorithm. So it fits on a slide, and you can write a large number of papers on it. That's actually quite generally true. So maybe 1 or 2 years ago, 2 new books came out on the CG method. So CG was proposed in 52 or 54 or so.
CG conjugate gradient.
Yeah. Slightly, I guess just after Lensschutz published his paper on the Lensschutz method for eigenvalue problem. So early 50s anyway. So So the interesting thing is that even though the algorithms are very simple, their analysis is not. But anyway, this is the linear system you want to solve. You have this residual. You normalize that. You call that V1. Remember, V was going to be this matrix that has an orthonormal basis for all these vectors. And then you do what is called the Arnoldi recurrence. And this is the same thing you would do if you use what is called Arnoldi's method for eigenvalue problems. Okay? So you take your latest V that's been normalized, you multiply by A. You just orthogonalize that. So this is a projection, and then you subtract the projection from the previous vectors from there. So this is just an orthogonalization. And then you normalize, and okay, that's your new V, and you go on. And at every step, right, you solve this small least squares problem. So how you go from this one to the previous one is basically linear algebra. I didn't really show it. But essentially it means you solve a least squares problem of size m plus 1 by m. And rather than actually solving this every step separately, it turns out you can, in a nifty way, update this as you go. So that makes it kind of a little bit cheaper. And the other nice thing is that the residual, the norm of the residual of this least squares problem is the same, at least in exact arithmetic, as the norm of the residual of your original problem. So that's nice because it means that you don't actually have to update the solution and compute the residual to see how well you're doing. You kind of get that for free. Okay, and then if you're happy with your solution, you can kind of, okay, you update the solution, so your new x is x plus. So this is your z essentially, and then you can update the residual as well.
So just
Yeah.
that second step is the only, that vk plus 1 tilde equals a vk, that's the only still part of it. The matrix vector, the second step.
Well, yeah, so that's a good point. So mostly we say for these Krylov methods that this is the most expensive step. And if you were using what is called a preconditioned problem, let me kind of show that actually. So in some cases, if ax equals b, we're doing an iterative method. So in iterative methods, you're interested in two costs. One is how many iterations are you going to do, and the other is what is the cost of each iteration, right? So kind of the same actually as in Monte Carlo, right? How expensive is a step and how many steps you need to do to converge. So if it doesn't converge fast, we typically solve a slightly different system. And I'll come back to this in a moment. But so you'd find a p such that convergence for p times a is much faster, but multiplying by p is still cheap. So usually that's considered as the most expensive step. But in GMRES, this is not completely true if you would do many iterations. And if you've solved eigenvalue problems using the Arnoldi method, you know it's the same thing, because every new vector has to be orthogonalized against all the previous ones. So m steps of your algorithm takes m matrix vector products or m applications of some operator, but it also takes roughly half m squared orthogonalizations. So of course, if m increases, at some point that actually swamps the cost. And that's why in practice you wouldn't just iterate with this algorithm until you've converged, but you do some number of steps, compute a new approximation, and then restart. Or actually, there's much smarter things you can do than just restarting. But that's another talk. But one thing that is also quite important to realize here is that if you write this out kind of algebraically, what you see is you build a search space, you project your large problem on the search space to get a small problem, and then you can use whatever standard methods we've been working on for small linear systems and later on for small eigenvalue problems, just from LAPACK and so on. So you can use very standard methods after that. So building this search space and the projection is really to reduce a large problem that you couldn't do using standard methods to a small problem that you can. So why would this converge? Okay, so we compute the best approximation in this search space, but if I have a problem to solve that has 100 million degrees of freedom, would we really expect this to converge in 50 steps, even if I find the best approximation in that space of 50 steps, right? So why? Now, unfortunately, that's not always true, but in many cases, we can make these methods converge quite fast. So why is that the case? Well, so this Krylov space, as I already showed, is a space of polynomials, and that means it inherits the approximation properties of polynomials on the real line if you're talking about a Hermitian problem, or the complex plane if you have a general problem. So how is that? So I'm going to make a few simplifications here that are not required. I mean, the methods don't care about this, but it makes my explanation a lot easier. So if A is diagonalizable, and so for Hermitian problems that's always the case, right? I can write A as V. In this case, V has as its columns the eigenvectors of A times, okay, the diagonal matrix lambda with the eigenvalues times the inverse of V. And of course, if V is a unitary matrix for a Hermitian problem, then V inverse is just V star. So what happens if I take A squared? Well, if you write this out, you just get V times lambda squared times V inverse. And more generally, for A to the power K, You just get the kth power of the eigenvalue matrix. Nothing else changes. And this matrix is diagonal. So what does it mean if I apply a polynomial to A? Well, I get all these things. I can move all the V's to the left, all the V inverses to the right. And I get the same polynomial in this eigenvalue matrix. But this matrix is diagonal, so really what that means is I apply this polynomial to every eigenvalue individually. So what does a polynomial do to a matrix? Well, this is what it does. It keeps the same eigenvectors, but you apply the polynomial to every eigenvalue. So just as a simple idea, right, if I'm solving a linear system, I want my residual to go to 0. And we saw that the residual is a particular polynomial. So if I can find some polynomial that maps a residual polynomial, right, that has this normalization that it's 1 at the origin, that maps every eigenvalue to something really small, so it's small over the region that contains the eigenvalues, I would have a small residual. So we can analyze these methods in terms of what polynomials do to regions of the complex plane. And eigenvalue problems, we can apply some of the same tricks, right? So let A have this eigenvalue decomposition, and let the spectrum be contained in some region of the complex plane. If I can find some polynomial Pm-1 that's approximately 1 over t for that region, right, then if I apply this to A, then I have an approximation to A inverse. Okay. Now, you can already see, right, it has to be approximately 1 over t. So this already tells you that very close to the origin. It's a relative thing, right? So if you, it's the really, what are the largest eigenvalues, what are the smallest? But you can imagine that very close to the origin, right, things get harder, right, because 1 over t blows up. So in terms of the residual, so if I write the residual in the eigenvector basis, and again, this is something you've seen, right? So when we looked at diffusion Monte Carlo, you would also, I have some initial state, right? I write it along the eigenstate, then my time steps are really just applying these matrix products to it, right? This is exactly, in many ways, the same thing, except in addition, we apply some polynomial to it. So I decompose my residual along the eigenvectors, and I apply this polynomial. So what am I going to get? So the rho I are the coefficients of the eigenvectors. They're multiplied by this polynomial in lambda, which is roughly 1 over lambda. And then, I multiply by the eigenvectors again, right? So that's just multiplying by this p, polynomial in lambda, and then V inverse. And that's just, well, approximately, because it's not exactly 1 over lambda, that's just applying the inverse to that residual. And the residual polynomial will look like this, right? So what does the residual polynomial look like? Well, it becomes 1 minus lambda times this polynomial. So if this polynomial really approximates 1 over lambda, then you get 1 minus 1, right, and you get 0. Of course, it's typically not exact, right, so it'll be approximately 0. So when is life good? Well, if we can construct polynomials for modest m that will do this, then we're in business. Then our solver will converge fast. Now, it's important to keep in mind that this is analysis, right? But if you go back to maybe the 80s, people were really looking at methods that explicitly constructed certain polynomials. And then we kind of realized later on, so you saw the GMRES paper is in 86, that, well, we kind of threw that away, said, well, they all live in this space. If we do an orthogonal projection on that space, we get the best approximation anyway. So you get this polynomial too, or a really good polynomial. You just get it implicitly. You don't compute the polynomial itself, right? But for analysis, it tells us to a large degree what's going on. So, all right, if we can get this for modest m. Now, most problems are such that that's not going to be the case. So that's where preconditioning comes into the picture. But if we can find some region omega that contains the eigenvalues, that is nice, okay, and nice, well, one way of thinking nice is take a relatively small region, I'll show you some pictures later on, that is away from the origin, because getting close to 0 was a problem, right? Then, and so we have clustered eigenvalues away from the origin, then convergence will be very fast. Now, if we don't quite get that, in general, and there's more to say about this, we can still get fast convergence, but if you really get eigenvalues very close to the origin or around the origin, convergence will be terrible. So what do you do in that case? Well, these methods won't save you in that case, right? But that's what we call preconditioning. So we come up with some matrix P, and I'm going to show you an example, such that PA has clustered eigenvalues away from the origin, and the product with P is cheap. And of course, a lot of work has gone into, for all kinds of different problems, finding such matrices P. And just to kind of show for later on, right, the analysis of eigenvalue problems, if you do an Arnoldi-like method, is similar, right? So let's say epsilon is some small value, and we're interested in lambda I. So that's the eigenvalue I'm looking for. And let's say, okay, it has some distance away from all the other eigenvalues. If eigenvalues get very close, we'll see later on, we're in trouble anyway. So if I can find some polynomial that is 1 at this eigenvalue, or large, and small kind of away from it, then multiplying by this polynomial in the matrix times, in principle, an arbitrary vector, as long as it has some component in the corresponding eigenvector, we'll pick out that eigenvector. So it's the same thing. And so if you've ever tried to solve eigenvalue problems, you probably have found that if you're looking for eigenvalues that are on the outside of the spectrum, convergence is relatively fast. If you want to pick out an eigenvalue that's in the middle of a whole bunch of other eigenvalues, it turns out it is very slow unless you apply some additional tricks. And why is that? Well, if the eigenvalue is on the boundary, right, you only need a polynomial that becomes small kind of in one direction and it can blow up everywhere else. But if it's in the middle, right, it has to go down everywhere. And in fact, since a polynomial is an analytic function, that's in fact impossible. I mean, you can put, if your degree becomes high enough, you can put zeros at all these surrounding eigenvalues. But there's no polynomial that becomes uniformly small around some region where it's large. Okay, so all right. Now, the details of this are not important, right? But one thing I just want to point out is that you can find all kinds of convergence bounds. This is for the linear system, then based on the properties of those eigenvalues as points or regions in the complex plane. All right. Okay, so we want to compute those determinant ratios by a preconditioned iterative solve. And this will be efficient if the matrices are sparse. Well, for insulators, we can do that. And if they converge fast. Okay, now in general, they will not converge fast. So we need a preconditioner to make that happen. Now, it turns out that one preconditioner that, at least so far, has worked pretty well for us is what is called an incomplete LU. These were invented in the late 80s as well, or actually early 80s, I think. And the idea is essentially you do an LU decomposition, but as you do the LU decomposition, which would have order n to the third cost, you just throw lots of stuff away that you don't like. I'm not going into a lot of details, but essentially it makes the cost of computing them order n, or somewhere between n and n squared. And the ones we've been using are order n. And then LUTP is a particular version that was proposed by Yusuf Saad, the same Saad that proposed GMRES. Now there's some problems though. So if we just threw that at the system the first time, it worked well. But since we're moving those particles around, the matrix kind of degrades in a sense. And it means it becomes far from what is called diagonally dominant. And if you don't know what it means, just think about having most of the mass of the matrix on the diagonal or very close. So the particle moves kind of degrade the matrix. So we'll have to update the ordering of the matrix from time to time, because this ILU, this preconditioning, becomes unstable and then it doesn't work well. Now, the reordering is expensive, and computing a new preconditioner is expensive too. So we applied a few other tricks, so to speak, and I'll come to that. So one is we want to update our preconditioner very efficiently, at least for many steps, right? So if I'm going to solve 1,000,000 systems, think of if I have 10,000 or 100, say, well, okay. I guess typically we do roughly like 100 sweeps and throw 20 away. I think that was the rule of thumb, right? So if you have 1,000 particles, that's 100,000 systems to solve, and okay, it goes up from there, right?
More, yeah.
Yeah, well, that would be one step, yeah. So if you actually do something more dynamic or so, it gets yet much worse. Anyway, so we don't want to compute this thing 1,000,000 times. Let's put it that way. So we want to update this preconditioner. That was one part. We want to monitor the instability. So we want to know when we have to reorder the matrix, and then we want to do the reordering effectively. So those are kind of all steps that went in there. So if you want to write, this may be also a lesson, right? So if you want to write efficient methods for some of these problems, right, a lot of detail goes into making efficient algorithms. Okay, so first let's think of these updates. So suppose I have a preconditioner P, and it doesn't matter, earlier I wrote PA, but you can think of AP as well. So let's assume AP is nice. That is to say, it has this spectrum, the eigenvalues are clustered away from the origin. And I keep saying that, but let's give some example, right? So here are, for different test problems, like if you do a large number of steps, right, then the blue ones are the eigenvalues. This is the origin, it's right in the middle. So this is exactly what you don't want, right? It's all the eigenvalues surrounded by the origin. The residual polynomial is 1, right? So this, yeah, this is 0, it's right in the middle. Yeah. So it's a very good example of what you don't want.
Like a Slater matrix.
Yeah, are the blue ones. But of course, well, so it's important. You cannot really speak about the eigenvalues of the Slater matrix because in some sense the ordering of the matrix is arbitrary, right? So it's up to some ordering. So given whatever we took as orbital, and then wherever the particles were at some point, that's where the blue dots come from.
And you have black and red also.
Yeah, well that's what I'm coming to. So if we reorder the matrix to make it more diagonally dominant, you get the black eigenvalues. So the determinant wouldn't have changed, or maybe by plus one wouldn't be a change, by -1, but other than that there would be no change as far as the Slater matrix is concerned, or the determinant is concerned. But the eigenvalues, you can see you have fewer eigenvalues around the origin. You're not getting rid of all of them, but a lot of them now are clustered to the right. And then if we apply this preconditioner, so we look at the eigenvalues of A times P, right, we get this very nice cluster near 1. Now this is also a relatively easy problem, but anyway, so this is what we mean by clustering away from the origin, right? You want to go from here to here. All right, but computing this preconditioner is not free either, right? But let's say A times P is nice, so it has this red spectrum. Now you want to keep that, but I'm updating my matrix. So my new A is A tilde equals A plus, okay, this change in the kth row. So I can write that slightly differently. I can write it as A times, and then, okay, I get this rank 1 update of the identity. So what if I could compute a preconditioner that essentially is the original P, but then multiplied on the left by the inverse of this, right? So the nice thing is then that A times P is exactly A tilde times P tilde. So they have, the preconditioned matrices have exactly the same spectrum. So if the first one is nice, the next one will be nice too, and I can essentially just keep that up. Now it turns out that we can do this almost for free because what is in here, so what does this inverse look like? Okay, it looks like this thing, well, okay, it looks like this thing, where U is, well, the same as it is here, and W is this. So this you've already computed, right? Because 1 plus U transpose A inverse times EK was exactly the determinant ratio you were after. So you get that for free. And this one you've already solved for as well. So computing W costs nothing. It's all stuff that you already have. So this is a very elegant idea. The only drawback is, so you're not going to compute this P tilde explicitly, right? You just keep your P, and you save W and U transpose. So now as a general idea, this is being used in optimization for a long time, but not with exactly the same purpose of kind of keeping these eigenvalues. Did it? Ah, okay. So I should also say, if people have questions, feel free to interrupt me. It's distracting. All right, so we don't compute this explicitly. We just keep our P, and W and U needs to be saved. And so this will give us, at this, because computing this thing is essentially for free, we can update our preconditioner very cheaply. The only thing is, of course, that every time now I multiply by my preconditioner, I multiply by P, and then I have, one dot product and one vector update. That's okay, but if I do that 1,000 times, right, I have 1,000 of them. So the cost of applying my preconditioner goes up slowly. And so at some point, that's actually more expensive than just computing a new one, right? So periodically, you just recompute your preconditioner, right? So as soon as the increasing cost of this sequence of products becomes more expensive than recomputing your incomplete LU, you just recompute the preconditioner from scratch. Now, it's not, you don't know exactly when that'll be because this cost is not so easy to know exactly, but you just take some, reasonable values. All right, the other thing is, okay, so you can recompute your preconditioner, but if this matrix degrades, essentially when you have, for example, all these eigenvalues around the spectrum, that actually shows your matrix is far from diagonally dominant. This preconditioner P becomes unstable, so it gives garbage results, right? So once in a while, not only do we need to compute a new preconditioner, but we need to update the ordering of A. And okay, so what is unstable? So if you throw away stuff while computing your LU decomposition, right, you can write A as LU plus R. And then, okay, the thing we're mainly after, and if you want more details, you can read the paper, is this thing. We want this thing to be small, but of course computing this thing is horribly expensive as well. So this is being used by people to kind of analyze preconditioners, but it's not something you want to compute you want to compute for your actual matrix. So one way we can do this now, multiplying by A times and then LU inverse, so that's just U inverse, a forward and backward substitution with a sparse matrix. We need to do that anyway in the Arnoldi recurrence. So again, we can do this very cheaply if we apply it only to the Arnoldi vectors, the vectors that we generate in the GMRES sequence. So again, we get this roughly for free, and then with a little bit of work, you can show that even if this is huge, but this is small, you're safe. So this is really the only thing we care about. If this is large, but this is small, then over the space in which we're computing a new solution, it was not unstable. So there might be some v's for which or there might be some vectors for which it blows up, but we can show they're not in that space. So again, so this is cheap too. And then, okay, there's the reordering algorithm, and it's just a greedy algorithm we picked up from another paper. And essentially, you pick a particle, you find its closest orbital, you pair them up, you do the next, the next, and the next. There's a few more twists to it. So it's a greedy algorithm, and it can be far from optimal, but usually quite effective. And there's some other algorithms for improving this that we've also tried, and they're not really better, so we didn't go on in that. But it's relatively expensive. So it's order n squared cost to do this. It depends a little bit on, right? If you find out that you only need to swap, two particles, then of course the cost is very small. But
since the particles are moving slowly, once you do it at the beginning of the calculation, can't you just keep updating it?
Well, well, that's the thing you should do. Okay. So we do that now. So but I wasn't done for this paper originally. Yeah. So since the particles only move a little bit, what you really want to do is do a small incremental update. And by incremental, I mean you take a few nearby particles and orbitals and you swap things around so that it's nice again. And that has the advantage that the cost is constant. So even if you do that every step, it's an order n cost for a whole sweep. And so it's better than this one because, well, if you would do this only a fixed number of times per sweep, then the cost would be n as well, right? Because it's some number times n squared over n. But that turns out not to be the case. So it turns out that as n grows, you would have to do more and more reorderings. Not a lot, but anyway. So this is the effect. And so I should say, so the matrix we took here, just as a test case, we took the orbitals were just Gaussians with a certain, so e to the power minus k times the distance squared. And for this one, k is 1.5, which makes them very localized. This is k is 1/2. So they're much more spread out. And that makes the matrix much more ill-conditioned. And this is k as 1, which we took as our kind of generic test case. And you can see in this case, you still get very nice preconditioned eigenvalues. In this case, it's worse. You do not get everything back to the right half plane, but having a few outlying eigenvalues doesn't really matter for Krylov methods either. And you can think about that. If you have a polynomial of degree, say, 20, you can just put zeros at those few eigenvalues and then use the rest of your polynomial to make this small. And that's effectively what the method does. Again, you don't compute those polynomials explicitly, but you can show that that would be...
So you mean if you have 20 iterations in the Krylov
Right.
sequence, you could tolerate 20 eigenvalues that are close to the origin?
Well, probably you want more than 20 because, yeah, so the idea is let's think of one. So what will happen if you have one eigenvalue that is really annoying, right? So initially the method will converge poorly, but at some point, you give a modest degree polynomial that is small over the cluster and just puts a 0 at this one eigenvalue, and then it's gone. So that is effectively what is happening. But yeah, if you have 20 annoying eigenvalues, you want 20 plus something.
Okay. Right.
Of course, if the annoying eigenvalues are very small, close to each other, then of course you can get them with 1, 0. So So I want to show you some results. So we took a very simple modest problem. So it's a BCC lattice with Gaussian orbitals. We took k as 1. We looked at other k's as well. The size of the cube is about 2, and n here is 2 times k to the power 3 particles, right? So you have your cube, and then you have like a cube that's offset by 1, 1, 1 essentially from it. That's your box. Now we're doing things approximately. So one of the things you want to check is also the statistics. We're not just the scaling. That's in the end what we're interested in. But if doing things approximately would give you large errors, then things would not be good, of course. Okay. So what can go wrong? Well, we're just looking at those acceptance ratios. So the only thing that can go wrong is you make a wrong step in your metropolis algorithm. So if Q is the probability computed with, say, the standard method and QA with the approximate method, then, okay, this is the difference. So if both of them are larger than 1, both will accept, no problem, right? If both of them are very small, and only if your random number generator would generate a number smaller than both of them, right, they would both accept. So really it's the difference between those two. So as long as those are very close together, right, the probability of a wrong decision is very small. Okay, so we look at this, so for a particular step, the difference is less than 10 to the minus 4, we call it an extremely good step. If it's less than 10 to the minus 3, it's very good. If it's less than 1%, it's good. And so, okay, so you can see the extremely good steps are all 99.5 something %, right? And the good steps are all at 100. So the probability of making a mistake is very small, right? It's in the order 10 to the minus 6. And the acceptance ratios were all, between. So my standard rule was 20 and 80, but I guess between 20 and 80 is what you want. I mean, you said 10 and 90, I don't know, but so it's something like that, right? So the acceptance ratios were fine, which is just tuning the step D that you take, right? So let's look at the algorithm or its cost, right? So the number of GMRES iterations should not go up substantially as n grows larger, right? So this is 686 particles, 1,024 up to like 5,000. I mean, now I should also say the iterative algorithm could have gone much farther, but at about 5,000, we couldn't find a workstation that could do the standard algorithm, right? So apart from just better scaling of being cheaper, there's other advantages too, right? Not having to carry a dense matrix around and so on saves a lot of memory. So you can see initially it goes up a little bit, but then it levels off. So the number of iterations is essentially constant, so that's good, right? So there's no increase there. Now, okay, in order to compare the number of non-zeros in your L and U factor, so if that would increase, right, it would mean the preconditional gets systematically more expensive, so that would be bad too, right? That would again increase a cost that makes it larger than n squared. But you can see they're roughly on the same order as the sparsity of A. I mean, there's some tuning you can do in computing them, and they stay constant as well. So that's fine as well. So the number of reorderings per sweep is going up slowly, and that means that the scaling is not quite at n squared. And there were a few other things that we did not in the best way, like the choice of when to switch from updating the precondition to computing an ILU. I mean, that's a completely easy to fix, so that's fixed now, but it wasn't done when we did this. But we only realized that afterwards. So these are the times, right? So the statistics are fine. These are the times. So you can see for small problems, the standard method is better, but at roughly 2,000 or 2,500 particles, you get kind of, or the 3,000, somewhere in between, right? It switches, right? So the sparse algorithm gets faster, and then, okay. And now the other thing I should say is that, on the one hand, QMC people have worked on optimizing a lot of steps, and in this sparse algorithm, we implemented things, in a reasonable way, right? It wasn't done clumsily, but we certainly didn't do a lot of optimization of the different steps. So each of these numbers can easily be improved probably by a third, taking off 30% or so. But the main thing we were interested in is the scaling, right? So the standard algorithm, if you take these numbers and you do a power fit, you see that the scaling is close to 3, and of course we know theoretically that as n increases it has to go to 3. And the new algorithm is slightly worse than 2, right? So we kind of, in terms of improving the scaling, we really did that. And we know roughly, if we do this incremental reordering like David just mentioned and what's implemented already, and we fixed one other problem, then we're really at 2. Okay, so this is the same in a graph. So there's all kinds of things, right? You go from one implementation of some package to another one until you've really done everything. It's kind of Amdahl's law, right? But now in fixing software. Until you've done everything, right? You're not going to get everything at the right efficiency. So better data structures and reducing some overhead would easily get us 20%. This is something we measured, by the way. It's not just my rule of thumb. So like I mentioned, updating the cheap preconditioner can be done better. Improving the reordering, so this is now done. So we now have an incremental local reordering. And there's other ways. We can use smarter solvers as well, and I don't want to go into too much detail, but there's smarter things in terms of the solvers. So kind of to summarize at the end of this part, right, so we did improve the scaling significantly, and the next steps really are, can we get below n squared? Now, to get below n squared, what it means is you have to somehow solve the systems approximately without doing even like one matrix vector product, right? So it means that we have to do something locally that we can compute that has fixed costs and that has to work most of the time, at least order n of the total number of steps. So that's something we're working on. And we're looking, so, and part of that is better preconditioners. We want to test on several realistic materials. This still needs to be done. I mean, so this was a very simple standard problem or test problem. And then for metallic systems, right, we cannot get the matrix sparse, but there's nevertheless other things that can be done. So one thing to keep in mind is what makes these methods n squared rather than n to the third is that the matrix vector product is order n cost. So for a dense matrix, if it has enough structure, or it means that if it has enough structure after maybe you throw small stuff away, right, so you massage it into the right form, in some cases very fast matrix vector products are possible, right? They could be n or n log n or something, but for large n, n log n is essentially the same as n, right? So that is something. And so the other thing is how to represent, you know, the basis functions and the matrix and so on. So there's other things that can be done. Okay, so some good reading. So this is the paper that came out of this. There is some stuff on linear solvers if you want, and eigenvalue problems and a bunch of other things on my webpage, so you can do that. And then two well-known methods on iterative methods are this one by Henk van der Vorst and the other one by Yusuf Sand. And there's actually, if you go to his webpage, this is the newest one, but there is a slightly older version available as a PDF. So if you don't want to spend the money, I probably shouldn't say that, but well, if you want to check the book out first, I think he keeps it because he's annoyed by how expensive they've made the book. So it's not that expensive, but it's more expensive than he wanted it, I guess. Anyway, so this is the first part. Any questions? Yes?
So you might not get your own figure. You have sometimes random distribution of your pipe. So you actually based on the periodicity or some legislature. In general, we have some kind of so random and disorder, some disorder.
I'm not sure I understand exactly, but I mean the particles are at random positions.
Try to rephrase the question.
So the lattice in this case is fixed, but the particles move around, so they're not on this beast.
Not moving, just a random fixed in this case. So I was wondering still you can actually use your techniques in that case, but without doing any specific basis.
I'm not sure I understand your question. Okay, sorry. Yes?
You said, suppose there are 5 particles. You change only one particle.
Right.
And you consider the ratio of this determinant. Slave determinant.
Right. Yes.
Generally, there are the 5 particles move all together.
Well, so the way that it was written originally, right, you could move all particles at once if you wanted to. So I guess if you would move all particles, I don't know if you could still use this, but if you move 5 particles, it's no problem. So you just have 5 systems to solve. But, and there's a slight variation because you have to solve the second one with taking the first move into account. Well, no, actually, you could solve all 5 of them at once. So yes, if you do, as long as you move a few particles, you can certainly do this. If you move all particles at once, which I think some people are doing, then I don't know if this would still be a good idea. You may have to do something else. But if you move them, but I think, well, I mean, David really should answer this question. I think the reason for moving only one or just a few is that it's much easier to make your acceptance ratio relatively good. So if you move all particles at once, I think what happens is that if you move them relatively, well, far as a relative term, the acceptance ratio becomes very slow. So you're moving them very small distances then. And so it takes a long time, I guess, to decorrelate the system. But I mean, that's not my area of expertise.
Depends
But
on the wave function. I mean,
right.
With the Slater-Jastrow wave function, with the Slater determinant in particular, since it breaks down into columns for each particle separately, you can move each particle one at a time and decide whether you accept or reject that particle move before you make the next one. And this makes you can move much further in phase space, much faster. This goes back to classical simulations too. What breaks this is when you go to a backflow wave function that I talked about, then all the columns get coupled together and you lose this ability to do this, actually. So as you get better wave functions, actually, you might have to change the algorithm.
Okay, well,
Yeah.
that keeps us going, right?
Yeah.
That's the next grand. But yeah, moving a few particles is no problem.
Produced by OCE Atlas Digital Media at the University of Illinois, Urbana-Champaign.